Welcome to This Explainer. Okay, today we're jumping right into something you have probably walked past 100 times without even giving it a second thought. When we talk about solar power, we almost always picture those sleek, shiny solar panels soaking up the sun on a roof, right? But today, we're focusing on the true, unsung hero of renewable energy, the solar inverter. Far from just being some boring gray metal box mounted on the side of your house, this device is the absolute mastermind of the entire solar power system.
So I really have to ask, what actually happens inside that magic box? I think most people kind of just assume it passively funnels electricity from the roof straight into the house. But the reality is so much more intense than that. Inside that enclosure, you've got complex, microsecond-level computing happening nonstop. It is this active, highly dynamic brain that's constantly monitoring, tweaking, and communicating with the grid to keep your lights on and your house completely safe. The stakes here are incredibly high, and honestly, the engineering required to pull it off is just spectacular.
All right, let's dive into this. The core conflict at the heart of every solar setup is basically a giant language barrier. See, solar panels speak direct current. The electricity just flows one way. But your home and the larger power grid, they strictly speak alternating current, where the current is rapidly reversing direction. If you literally just plugged DC solar panels straight into your AC house, well, absolutely nothing would work and you'd probably fry your appliances. The inverter has to step in as the ultimate real-time translator. To figure out how this magic box actually works, we're going to follow an electron's journey through 4 distinct hurdles. 1. The translation challenge. 2. The efficiency challenge. 3. The integration challenge. And 4. The safety challenge. Starting off with number 1, the translation challenge, converting DC to AC. The electron really faces a gauntlet here. First up is the DC input, where the raw solar energy comes down the cables. Then comes the heavy lifting, the actual power conversion. Inside the inverter, you've got these power electronic components, specifically things called IGBTs or MOSFETs, acting as insanely fast switches. They take that flat DC signal and literally chop it to pieces, flipping the direction of the current back and forth at lightning speed. But that chopped up power is super messy at first. So step 3 is harmonic filtering, which smooths out all that high-frequency noise. And finally, step 4, you get a nice, stable AC output ready to run your home. Now, what's really interesting here is the actual H-bridge circuit topology that makes all of this possible. You see those components labeled S? Those are the high-speed switches we were just talking about. By perfectly timing the opening and closing of those switches in a diagonal pattern, the inverter rapidly flips the voltage polarity. It's this highly orchestrated, ultra-fast mechanical dance that actually creates the very foundation of an alternating current out of a flat direct current. Look at how this transforms. When the current first leaves those high-speed switches, it's pretty ugly. It looks like these blocky, stepped waves. Way too harsh for your electronics. But once it passes through the inverter's filters, those jagged, blocky steps are beautifully transformed into the smooth, rolling, perfect AC sine waves you see right here. This waveform is exactly what the utility grid provides, and it is exactly what your fridge, your TV, and your laptop need to run without a hitch. Okay, moving to section 2, the efficiency challenge, maximizing power with MPPT. Think about it. The sun doesn't just sit still in the sky. Clouds roll over, temperatures spike, shadows stretch across your roof. The inverter has to act as a brilliant problem-solving brain to adapt to those constantly shifting conditions. And yet, despite all those variables, modern inverter technology hits a staggering 98% conversion efficiency. 98%. Older traditional inverters used to hang out around 90%, but today's cutting-edge systems make sure that almost none of your precious solar energy gets lost as heat during the conversion. It is a massive engineering leap. So how are they actually pulling that off? Well, it's through maximum power point tracking, or MPPT. A super common way to do this is with what's called a perturb and observe algorithm. It's kind of like your car's automatic transmission. As you drive up and down hills, the transmission is constantly shifting around to find the absolute most efficient gear, right? The inverter does the exact same thing. It intentionally perturbs or slightly nudges the operating voltage, observes whether the power output goes up or down, and then just continuously adjusts. It's actively hunting for that absolute perfect sweet spot to maximize your power, every single second of the day. Let's jump to section 3, the integration challenge. Synchronizing with the grid. Making AC power is one thing for sure, but sharing it, entirely different story. The utility grid is a very strict, completely unforgiving partner. To connect to it successfully, the inverter has to perform this incredibly delicate dance. It absolutely must match the grid's voltage, it has to match the frequency perfectly, and it has to perfectly align its phase angle. It's basically like merging your car onto a high-speed highway. You can't just blindly swerve into traffic. You have to match the speed of the other cars, find a gap, and align perfectly for a seamless merge. The inverter is constantly doing this delicate synchronization with the grid. If it's even slightly off, it creates serious grid disturbances.
Let's move to our final point, Section 4, the safety challenge. Anti-islanding protection.
This part isn't just about efficiency. This is absolutely crucial because it's about protecting lives. Imagine a massive storm rolls through and knocks out the main power grid. The utility company thinks the street lines are totally dead, so they send line workers out to safely fix them. But if your solar panels keep generating power and your inverter just keeps shoving that power backward onto those local lines, your house just created an unintentional island of live electricity in a sea of blackout. That backfed power is a severe, literally life-threatening shock hazard to the folks working on the lines. To stop this from happening, the inverter has to play detective. It basically relies on two main detection methods. Passive checks mean the inverter is just keeping an eye on the grid, watching for sudden drops in voltage or frequency. But say your home's energy use perfectly matches your solar output at that exact moment. A dropped grid can actually be kind of hard to notice. That is where active checks come in. The inverter will literally inject these tiny, harmless disturbances into the current, something like a slip mode frequency shift. A strong active grid absorbs that tiny nudge easily, but if the grid is down, that little nudge causes the frequency to wildly destabilize, and it instantly reveals the hidden island. And the absolute most critical point is what happens the exact instant that island is detected. Fast shutdown. Boom. The inverter has to immediately sever its connection to the utility grid. We are not talking about taking a few minutes or even a few seconds here. When the grid drops, the inverter must cut the connection in mere milliseconds to guarantee not a single drop of stray voltage makes its way out to those power poles. It is a rapid, completely non-negotiable safety mechanism built into every modern system. So as we wrap up this explainer, I really want to leave you with a thought. Next time you look up at those seemingly simple solar panels soaking up the sun on a roof, are you going to remember the microsecond level computing happening right there inside the inverter? From chopping up and translating raw DC into smooth AC, constantly hunting for maximum efficiency, flawlessly merging onto the utility grid highway, and literally protecting line workers in milliseconds, the inverter really is a total marvel of modern engineering. Thank you so much for joining me today to unlock the magic box. Stay curious.